Hi, good morning, and welcome to the ZP vlog and podcast. So, sorry, it's not the vlog and podcast, it's the Developers Zone. We do this every Thursday at 8 a.m. London time, and it's really trying to be answering questions that have come in from, let's say, the community and people interested in getting into biosensors and wearable biosensors. Also blood gas analyzers and also in vitro diagnostics. So let me go a little bit quick and just say that we do have the ZP Academy. So today I will mention amperometry, potentiometry, impedance spectroscopy, voltammetry. If these terms are not familiar to you, try out the ZP Academy. But there's also quite a few videos on our YouTube channel about this. But webinars, for example, every Thursday at 8 a.m. London time, we try to do this webinar specifically for people interested in our sort of core technologies, let's say, but we also do webinars around our other products like FoodSense. Collaborations, there's definitely collaborations going on in the UK and in Norway, in particular with universities, and collaborations really work best, where there is actually a source of sort of funding for it. Otherwise, it's not really sustainable. Jobs, we've definitely hired some new people in Norway of recently. We do have our ZP Developers on website, and we do have our workshops. I also want to just say that we did add an extra workshop because over the last couple of weeks, we've been doing webinars, especially for people interested in wearables. And one group in Turkey mentioned that September was too late for them, so we did put a special one in for them for August as well. If a link appears, I've already put it underneath the video, but we do have a new webinar in August in the UK. There is definitely ones going on in September in the UK and Norway. We do have a big conference running also in Norway in September. So this is the large conference. And the large conference, really, the whole theme of it for me is that so the future of humanity is the fact that we are going to measure a lot of things, both in our environment, on our bodies, in industrial applications, and sensors are kind of the edge of the clouds, and so with a sort of smart edge. And so at ZP, we're really working on that thesis, that philosophy. So link to that anyway. So question number one and question number two, I've sort of combined them, but question number one says somebody wants to make a portable a portable IVD system. Portable also means sort of point of care, rapid diagnostic testing. These are kind of synonyms for portable. So they want to do PO2, partial pressure of oxygen, partial pressure of carbon dioxide, pH. Do we have the sensors? The quick answer is yes. And it's probably also worth saying that we do a newsletter. I never really talk about it in the webinars, but we do a newsletter. I'll put a quick link here. I may not have linked to it underneath the video, but we do a newsletter. It's probably worth signing up to that because things mature, things change with us. And the companies that are kind of, we're a kind of constant innovation company. So some of these sensors, the new applications open up. Somebody was also looking for a partner for an IVD electrolytes in samples like serum, whole blood, plasma, urine. On top of that, I could put tear film and breath. We've covered all the matrices in our time. So question number one and question number two are actually linked. Question number three is a kind of is an ongoing discussion that we've been kind of having with some teams in a team in Southeast Asia around glucose and lactate, and I will talk about that today. Somebody was asking about our HyperValue carbon electrodes, whether they work in the flow cell. The quick answer is yes, and I'll give you some background information on that. Somebody else was asking about our potentiostat. So our potentiostat is really an R&D platform for us. So if you're going to do biosensor development, at some point you have to have enough sensors, or enough data rather, to really understand that what you're looking at is sort of, let's say, real as opposed to just some artifacts. And time is really valuable. So if you can do essentially 5 experiments I keep saying 5. If you can do 6 experiments at once, it's just, in simple terms, per minute, it's 6 times more effective. Some of you also want to know how to get a staircase experiment. And there's actually a really nice YouTube video online. And so many of these questions are actually linked to each other because question number 2 probably involves some glucose. Question number 4 about flow cells. You can also talk about flow cells and glucose there. question number 6, how to get a staircase experiment with a glucose sensor. We also have that. Question number 7 is the sort of I wouldn't say the oddball, but it's the outlier. This one, somebody's asking about one of our wafer holders, so I will discuss that. And then also linked really to wearable biosensors. Somebody's interested in our microneedles and whether they could be put onto humans. So I've combined questions number 1 and questions number 2. And I've also written a bit of an article about this because our sensors could, I suppose, fundamentally could be displayed in 3 ways. They could be wearable, they could be what we call point of care, or they could be used on benchtop instruments or desktop instruments that I would kind of term as a blood gas analyzer. And the nice thing about it is, for those 3 applications, at least the formulation stays the same, and in at least 2 of them, the sensor absolutely can stay the same. So we do have pH, we do have electrolytes like sodium, potassium, chloride, and calcium. We do have PO2, and we do have glucose. So glucose will keep reoccurring today. It's a reoccurring theme in my life, and it's a reoccurring theme at Zimmer & Peacock. I've written a bit of an article about this, and I have put the link underneath here. But in that article, I sort of discuss, I think something that happens quite a lot is people come to us and say, like your sensors, you guys are really innovative, and I appreciate those comments. It's really, nice of people. And then they're like, I want to use your sensor in our product. But see, the question is, there's so much more to that, because if we just give you a sensor, that's fine. But really, a question that kind of comes out is, well, what's your accuracy? And really, if we give you a sensor and you put that in your system, our accuracy is actually a function of your total system accuracy. So when people say, I want you to know your accuracy, well, actually, our accuracy is really part of the entire system. Especially in a blood gas analyzer, where actually a blood gas analyzer, I would slightly argue, is one of the easier applications in life because it can be very forgiving. So let me sort of illustrate that. First of all, if you're making a point of care device, you're not going to do in situ calibration. But if you're doing a blood gas analyzer, it's very common to actually have solutions of known concentration to be able to flow over those sensors and periodically recalibrate them. But that is a discussion that needs to take place. And, at ZP, part of our business model is consulting. So we would consult on what does that calibration solution have to look like? How often should you calibrate? What's the storage conditions for it? So calibration routine, but in the world of IVD, or rapid diagnostic testing, you really shouldn't be calibrating in the field. Now, whether you reuse a sensor depends on the application as well. So in the case of in vitro diagnostics, i.e. rapid diagnostic testing, you don't reuse a sensor. You put a sample of blood on there, or urine, or wherever it is, you get a reading and you dispose it. The reason being is it's actually, it's not about the reusability of the sensor. It's actually, if you reuse it, you have to prove that you've actually cleaned it, and you'd have to prove that you weren't creating a risk of infection for that person or the next person to use that sensor. But of course, in a blood gas analyzer, it's linked to point number 1 above. Actually, you can have wash routines. Sensor electronics, whether you're doing benchtop or handheld, the electronics will stay the same. I'll link to that. Method of analysis. It's not enough to say, we want a glucose sensor off you. Or a pH sensor or a PO2 sensor. We really have to talk about the method of analysis. And the method of analysis, again, would depend on the form factor, the total system that you actually have. Now, the method of analysis for us, luckily, the electronics in point 3 would support all the methods of analysis that we would want to play with. And then really importantly, especially when people are asking us, well, what's your limit of detection? For example, it's the signal. It's how you get the sensor out. Sorry, how you get the signal out the sensor. So an electrochemical sensor will give you a data point every time you essentially read it. So your frequency of save is really the frequency of data points that you'll get. But how you look at those data points is really critical to things like limit of detection. So essentially extraction of information from data, which I would also call signal processing. And then really importantly, people will come to us and say, right, you've got glucose sensors, but the conversation about how to integrate that into your tile system, which is covering the first 5 points above, is really it can be a big effort, let's say. So at ZP, we do actually offer the addressing of these 6 points as part of our kind of contract development, contract manufacturing, and consulting terms. So we have these as sensors. So that really accelerates the development, but then it just moves it onto an integration. Then there's an integration phase about, we have this, you have that, how do we make the two things essentially work together? Side note on electronics, we do have very tiny electronics. I've done this before, but that is my finger, and the electronics are very small. This is a glucose sensor that's actually being tested in what's called a sort of a staircase response. We just keep on adding glucose and the signal goes up. And the fact that the electronics are very small, size of my fingertip, we haven't lost anything in terms of quality of data. And I have put some links here, and those links will be underneath the video as well. And if integrating our electrochemical sensors into a portable device or a benchtop device, we would actually change the method of analysis, be it amperometry, voltammetry, potentiometry, impedance spectroscopy. We would change that really depending on your sort of requirements sheet. And requirements is really, again, it's a really consulting effort, because we have to discuss what can and can't be done, and what should and shouldn't be included in the requirements. The nice thing is that all these techniques can be implemented very easily on these electronics. This is a video that I have, and I've also got to put a link to it as well. But in this video, it happens to be a signal that's quite like a glucose sensor. So glucose sensors tend to give kind of an amperometric response, especially glucose strips. If it's a CGM, the signal can look, that's when I say CGM, I should say continuous glucose monitoring, the signal can look different. But in this video, I show you that for the same data, depending on the way I look at that data, I will get a different limit of detection. And that's why it's so important when people come to us and say, oh, well, can I use your sensor in my point of care device, in my benchtop system? The answer is yes. And then, well, what's your limit of detection? Well, the answer, actually, this video illustrates it quite well. We've actually improved the limit of detection by a 10x in this video, just by changing what time points we actually use in the extraction of the signal from the raw data. It's very hard to kind of essentially explain that, but I think a lot of people who follow along with this stuff will see it. Here I use quite a broad window. Here I use a window that's just near the front of the sort of data set, and then here's another window where it's actually at the back end, and depending which one you choose actually really affects the limit of detection. So I quite like that video, and I have got a link to it here, so it's probably worth reading, especially if you really are interested in blood gas analyzers, or you are interested in sort of portable devices, and also if you're interested in doing wearable devices. Question 3 is really a kind of continuation of some emails and conversations that we've been having. So at ZP, we do make wearable sensors. We do these transdermal ones, we do these microneedle ones. Microneedle is question 8 as well. It does come up today. We do also, we've done work at least in sweat and sweat patches. We sell the sweat patch online. Something that I'm not going to talk about today is, we do have a big effort in implantable sensors. And I really quite like this implantable sensor, because this is a really total system, where we've put power, electronics, communication, and the sensor all integrated in one package, and that sort of program has easily had over €1 million spent on it so far. So a couple of questions, and I'll just read them carefully to make sure. So we do offer something that's called the HyperValue electrodes. We're basically just trying to do a high quality product at a low cost, and the only way we can do this is we use these HyperValue electrodes ourselves. We're the biggest users of them. Then we make a portion of the production available on the website. So it's the kind of volume that allows us to, you can't have low cost and high quality unless you have volume. We manage to get to volume. Here they're asking about graphene electrodes versus graphite electrodes. So first of all, we have built glucose sensors and lactate sensors on top of graphite. but then we do really what's called a generation 2 glucose sensor or generation 2 lactate sensor. I'm really not going to discuss it here. It has to be discussed in these workshops because it's 45 minutes of deep conversation, but it's not that hard. But the quick answer is we do it on graphite. It's a generation 2 glucose sensor. If you really want to know about that, it has to be at the workshops. We do have one in August. We do have one in September. Just a quick comment on graphene. We've not built a glucose or lactate sensor on top of graphene. And graphene, I appreciate, is, let's say, really popular. I'm not completely, and by the way, we do a graphene sensor, and I will have a link to it. I'm not completely convinced that graphene, well, I'm not convinced that graphene is this wonder material that's going to, it might solve the world's problems in terms of batteries and capacitors. I could understand that. But in terms of biosensors, you know, it's not offering an awful lot, but, you know, you can still get them from us and you can try and compare. Now, if I was getting into the world of glucose sensing and lactate sensing, I would actually be starting with platinum electrodes. I definitely have a HyperValue platinum electrode. The reason we use platinum is because one of the simplest mechanisms for detecting glucose is to turn it into hydrogen peroxide. Hydrogen peroxide is active on platinum, but it's very poorly active on things like carbon, for example. So I definitely have a HyperValue platinum electrode, and it is linked to in this. We do have these glucose strip activation formulations. Anyone who comes to our workshop, we give you a glucose active strip formulation. You pipette it on the electrode, you cure it for 15 minutes, you test it, and you'll see it works. So we do have that, and when we're doing that work, we're pipetting it onto HyperValue platinum electrodes, not the carbon electrodes. We do have formulations, the same formulation for lactate as well. I do have a slide on that in a minute. Somebody's asking about Sensit Smart. I think Sensit Smart can be used in the sort of proof of principle of wearable applications. I will discuss that. We do these, it sounds, you know, we do connectors, and these connectors are really, so the anapot is a potentiostat that we have the anapot, we have a sensor, the glue between the cable of the potentiostat and the sensor itself are these connectors, so they are sort of required. I want to go a bit quicker because I don't want to be sort of too dull on this. We do often, you'll see that we actually have two types of sensors or two types of electrodes. Some of them have this chloride layer, some of them don't have the chloride layer. I would prefer if people didn't go for the chloride layer when they first started. Now the reason this chloride layer is there is because a silver chloride electrode is really a kind of pseudo-reference electrode, because actually the silver chloride electrode is sensitive to the chloride in sample. So if it's blood and interstitial fluid, then the chloride is pretty fixed because it's about 135 millimolar in those samples. But if it's something like urine, then actually it's not fixed, and then you have to start thinking about chloride layers, because then we fix the chloride above it, but they're just not perfect. The chloride will come out of those electrodes. So when people are first kind of getting into this, I don't want the complexity of their benchtop data having two elements to it, one of them being, for example, lactate, which is the signal they want, and then another one being drift due to chlorides leaching out. And so that's why, you know, I try to get people to start simple and then build up on complexity. Glucose versus lactate. Our glucose activation solution is really kind of low cost. We definitely have videos online showing people how to do this, by the way. When I say do it, I mean use these solutions. The activation solution for lactate is basically 10x more expensive, and it simply reflects the underlying cost of the enzymes. So glucose strips, you know, and the diabetes market, you know, it's a $1 billion industry. Billions of products are made per year, and therefore the supply chain is very mature. I would say very optimized. It's just not the same for lactate. So the underlying costs in making a lactate sensor are higher because it hasn't had the 40 plus years of development and supply chain optimization that you do have in the glucose space. But we do have these sensors, these activation formulations, and here is a link. Sensit Smart can be used. We sell the Sensit Smart on our website. Here it is. You can use it in wearables. Now, when I say you can, I've sort of seen papers, but I was thinking the same myself, that if you can wear a smartphone, it is very kludgy. and really only good for, so let's say, publishing papers. If you wear a smartphone here and you put a cable, the sensor would go in the front of the Sense It Smart, and you put a cable between the smartphone and the Sense It Smart, then it's kind of a very kludgy wearable or portable potentiostat. The thing about the Sense It Smart is I'm really not convinced actually it is a device for doing your R&D upon. It's a device for sort of showing products concepts with, but it's not really the device I would say for R&D, but it is good for sort of product concepting, I would say. No disrespect to the product, I mean it's a good product, but this is something, sometimes when you're doing bench work you want something that's quite, it's big, you can put the solutions on it, it doesn't fly around the lab, etc. But it's very good for product concepting like this. Sense It Smart, I did get this directly from the manufacturers of Sense It Smart. They really like our HyperValue electrodes. And the reason they like our HyperValue electrodes, and I'm glad I actually put this note in here, these small potentiostats that are often USB powered, they have a more of a problem with compliance voltage. So the compliance voltage is this. If you, for example, are making a glucose sensor and it's a generation 1 glucose sensor, then you probably have to apply a voltage at your working electrode at 650 millivolts. Now, in order for that to work, the potentiostat's then applying another potential at your counter electrode, and that's the compliance voltage. But the power on a USB power potentiostat is actually quite limited. So if, for example, you had a carbon counter electrode, you may be applying more than -1 volt on the counter electrode, and the potentiostat could actually struggle. Whereas the reason that the manufacturers of Sense It Smart like our electrodes is because we use silver chloride as our counter electrode. So that means that the compliance voltage is closer to 0. And they told me directly that it actually works best, the Sense It Smart works best with our HyperValue range of electrodes, because actually we have silver chloride as the reference material. So we have a gold HyperValue electrode, platinum, carbon, graphene. The links are already underneath the video. To get going, I did say to these people, to get going on glucose you need a potentiostat. You need this connector to go between the potentiostat cable and the sensors. Electrodes, these are definitely the platinum electrodes. That's the enzyme activation solution, and there's the barrier layer. I do videos on generation 1 glucose sensors, and also I do cover this quite heavily in our workshops, and I did put an extra workshop specifically for a group in Turkey on in August in the UK for making sensors, and they could do this here. Question number 4, HyperValue carbon electrodes. Yeah, so I will. It's just basically somebody spotted our flow cell. So this is one of our flow cells. I definitely have a link that's going to appear in a minute and is also underneath the video. This is really a great guy called Andre, and he's just showing, that's the sort of top plate. These are the sort of microbore tubing in and out. And then he shows here he's using our HyperValue electrodes. So the quick answer to your question is it's definitely, this flow cell is definitely compatible with our HyperValue electrodes. He shows the pump, and he shows he's doing a cyclovoltammogram actually, but he's doing it in flow, and that completely understandable by me that it changes the cyclovoltammetry. And we could actually cover that in our workshops as well. Terrible spelling of the word potentiostats here, but so at ZP, we're contract developers, contract manufacturers of electrochemical biosensors. This really means that we need to have statistically significant numbers in order to make good decisions. So, if you're in an R&D phase, it's not unusual to make 10 sensors, 9 of which are good and 1 of them is bad. The problem is if you're not testing enough sensors at any one time, if you are unlucky enough to test a bad sensor, and that's the only one you test, then you're completely thrown off with what works and what doesn't work. So we need statistical numbers, and that's essentially why we ended up creating the EMA potentiostat. And then the question that came in this week was, is it is it 6 working electrodes and 1 counter electrode and 1 reference electrode? So the quick answer is no. It's actually able to run 6 true complete electrodes. So each channel is able to deal with a working electrode, a counter electrode, and reference electrode, and the potentiostat is not trying to share the reference electrode between all 6. So I hope that kind of clarifies the mode of operation of the EMA potentiostat. And I do appreciate you reaching out, and you did get a quote, so thank you very much for that. Question number 6 is one that's come through YouTube, but they were really cool because I said, look, can you send us a questionnaire? And they did, and so thanks very much for that. If you come to one of our demos, one of our workshops, sorry, you do make a glucose sensor, and then we sort of show you how we put the glucose sensor in a beaker like this. We start stirring. We start the potentiostat. You get what's called a charging current that relaxes, and after about 100 seconds we start adding glucose into this stirring solution, and every time we add glucose the signal comes up in a sort of, we call it a staircase response. I think really there is no one saying what this is really called, so I think, to be frank, if everyone starts using the term staircase response, it's fine. It'll become the sort of nomenclature for this. I also wanted to just, I'm just going to mute this because I do have a video, and we do have a link to this video at the very bottom of all the URLs on the YouTube video today. This is linked to, and it's literally a live demonstration of Andre doing the staircase. So, all the parameters are in there. He's added the first glucose step. It kind of comes up. You talk for a few seconds because basically we want it to plateau. I can see his arm reaching out, so he's getting some more glucose now, and then he's going to add it into the solution, and we'll just see what happens there. 1, 2, 3. There he goes. Hopefully he's doing it now. I might have to he's really getting a plateau, so he's really going for it. Let's say, let me just there we are. So look at that. I mean, it's really nice. So it's almost so first glucose response, second glucose response. I will fast forward a bit. Third glucose response, and that's the link. I've definitely put that link underneath the video. So the quick question to the person on YouTube about how do we do these staircase responses, and this is really important to the people who are asking about lactate and glucose. This video will be super useful to you. He is using the Anapot to do that experiment, by the way. Question number 7. This is the kind of at Zimmer and Peacock, we do a lot of manufacturing of biosensors. Sometimes we do it on wafers. So we have something called a wafer holder that allows us to do electrochemical deposition upon wafers. This is the picture. This is the link. This is the model of how the product works. So we kind of have this backside piece that has conductive. It has a conductive backside, so we can basically make electrical contact. We have an O-ring because we're going to basically put the wafer on there, and then we're going to put the front cover on, and then we come around with a whole bunch of hex screws, and we basically seal the whole thing together. So we can make electrical contact. The front is exposed, and I've got an image of it here. And you can do, it's essentially a sort of one electrode, so you need some sort of counter electrodes to it, but we've developed it for doing electrochemical deposition on wafers. And I just want to say that I also have asked the team to do a YouTube video on the assembly of this device, because I think the video might help people understand what we've got. So I just want to say that on Monday, Tuesday next week, especially this particular inquirer, subscribe to the YouTube channel, because you will see our video come up. The engineers are going to make you a quick video, so hopefully that will help. So we have a standard product, and we also have customization. If you've got something a bit special, then we're going to have to do a customization job on this. Question number 8 is really about microneedles for human use. Microneedles for human use are definitely covered in our August workshop that I have specifically put together for these particular people, so I hope you can attend. We are ISO 13485, so we develop medical, electrochemical biosensors for medical applications. We do have a Class 7 clean room for aseptic manufacturing. So we have a clean room. It's clean, but it's also monitored to make sure that it's bacteria free and pathogen free as well. The electrodes that we make available on our website are for R&D purposes only. It's not that they can't be medical devices. It's just, it's almost like a legal concern that you can't just put things on the web, say, yeah, do what you want. No, they're for R&D purposes only. If you look at the sales conditions for Sigma Aldrich, for example, or Merck Chemicals, you'll actually, when you read the sales conditions, you'll actually find out that those materials are for R&D purposes only. Nobody ever reads it, but it's for R&D purposes only. So you do need a separate agreement with ZP to use on humans. And these kind of commercial agreements, they have to be with companies that are legal entities. The companies have to be well funded. So if we're going to do work on human beings, it generally has to be either through a funded European project, a funded UK project, a funded USA project, or a commercial company that really does have the right kind of financing to do this properly. So we do make our microneedles and functionalize our microneedles in a very clean and controlled environment because it's aseptic. But we will not, I would say allow, because you can't control people at a distance, but the sensors that we make on sell on our web store are not for human use. You can buy them, but they're not for human use. We would do it with clients and, as I say, real projects, but not just off the web store. So for R&D purposes only. And I think most people can understand that, there would be literally you're sticking something through somebody's skin. There's a lot of, you're opening yourself up for a lot of liability. So it's not something that we can support unless it's through proper programs with us. I did say to these people, look, we got this big workshop going on in September. I think this is a really excellent workshop, by the way, because it's a 2-day workshop, really intense. And immediately after it, we also have the Scandinavia Sensor Summit. So essentially it's 4 days, which is very useful use of people's time. But they couldn't make it. So I said, look, actually, I did speak to the team and we'll hold one in August. So I hope you can sign up for that. And I've put a link to it here. So I think that's it. I want to say thank you very much. My apologies that I want to apologize for speaking fast, but to be fair, there was something like 8 questions there. So the person who came in on the Wafer Holder, subscribe to the YouTube channel because there'll be some new videos going up on Monday, Tuesday. Otherwise, as per normal, if you've got any questions, reach out to us at zimmerpeacock.com contact. We generally, questions that come in during the week get answered on the Thursday. So the next time round, if you ask a question between now and next Thursday, you'll probably see your answer appear in this format on the 20th of July. Okay, thanks very much. Have a good day and speak to some of you soon, especially by email. Okay, thank you very much.